So today we're going to continue talking about antiderivatives, indefinite integrals, and in particular we're going to pay attention to what are particular solutions. So this is a nice way to say we're going to do some story problems. So the key words are particular solution, initial condition, position, velocity, and acceleration. So the key idea we want to recall from yesterday is that two different antiderivatives differ by a constant. That is, graphs of solutions to this problem of the indefinite integral are going to be vertical translates of each other. And let's see this better with an example. So what we have here is we have the family of functions defined by x to the fourth plus c. So all of the graphs over here on the right are different graphs of x to the 4 plus c for different values of c. This top one is x to the fourth plus 3. We have x to the fourth plus 2, x to the fourth plus 1, x to the fourth. And the key thing to see about them all is they all have the same slopes everywhere. The only thing that differs is where they moved up or down, and that's what the c value really does. However, what often happens in practical problems is we don't care about all of them as much as what we want is a particular solution. So when we pick a certain value for c, that becomes a particular solution. And when we're given information that helps us find a particular solution, then this information is called an initial condition. So let's start by looking at an example. Let's find the general solution to the differential equation f prime of x is equal to 4x cubed and find the particular solution that satisfies the initial condition f of 1 equals 0. So by integrating 4x cubed using our power rule, we get x to the fourth plus c, which is our general solution. So what we have here is we have graphed several members of the family of functions x to the fourth plus c. And our goal in this problem is not only to find the general solution, but also to find the particular solution that goes through the point here at 1, 0. And so graphically what we're going to do is we're going to move the c value, this is the thing we can choose, around to see which solution goes through that point. Now all of these members of this family, they look pretty much the same because this c value, since it's added on to the end, all it does is it moves our graph vertically, it moves it up and down. And so by going through certain c values, what we can see happen is eventually, oh, we just missed it, we got to come back a little bit. If we pick a c value of -1, that's the one that's going to go through the point that we want. So for many functions, what it is you have this whole family, all these choices, and then by pinning down an initial condition, you can say exactly which one you want. The key is to remember that this is just a family of functions that all have the exact same slope, but since your vertical translations don't change the slope, it can be any one of those. So now algebraically, what we want to do is we want to figure out how we're going to use our initial condition up here in order to figure out our c value. So to find the c value, what we need to do is we need to use our initial condition that says, well, 0 needs to equal f of 1, which needs to be 1 to the fourth plus c. So I got this from the fact that I know my general solution is x to the fourth plus c. So solving this for c tells me that c has to equal -1. I just subtracted 1 from both sides. So the particular solution to this problem is going to be just x to the fourth minus 1. It gives us the graph that goes through that point that we wanted it to. So these ideas with initial conditions and antiderivatives are very useful when we want to solve motion problems. So let's review some motion ideas. So the first thing we want to recall is how different things like position, velocity, and acceleration are related. So the first thing to remember is that position, usually given by p of t, and as an example, let's say it's given in feet in terms of seconds. So t is in terms of seconds. Well, then its derivative is going to be velocity, usually given by v of t. And it's the derivative of position. Units are feet per second. And last we have acceleration, usually given by a of t. You know, there's not a lot of clever name choice for your functions. It's the derivative of velocity, and its units are feet per second per second. So here's a pretty standard problem we could solve with this idea. A ball is going to be thrown vertically upward with a height of 6 feet and an initial velocity of 60 feet per second. How high will it go? So what I'm going to do is I'm going to repeat this on the next slide so that we can fit everything on one page, hopefully. So one of the first things you should always do when faced with a problem like this is to try to draw a picture in order to give yourself a sense of what's going on. So on the graph here, what I've got is I've got height and time. And what I know is I started around 6 feet. The ball was thrown upwards in the air. It probably traveled for a while, and then I'm guessing it traveled back down because of gravity. So roughly speaking, the graph kind of looks something like this. It's going to kind of follow this motion. Step 2, what we want to do is we want to record what we know. So what we want to do is we want to go through the problem and think about things you know. So we've got ourselves a ball that's thrown vertically upward, starts out at a height of 6 feet, and starts with an initial velocity of 60 feet per second. So since this is a motion problem, what I know is I'm probably going to have three functions. I'm probably going to have P of t, which is the position. I'm going to have V of t, which is my velocity. And I'll have A of t, which is my acceleration. And what I'm also going to do is I'm going to measure all of these in feet, and t is going to be in seconds. And I get these from the problems. I've got height measured in feet, where I get feet from, and seconds, so everything can be the same there. The next thing I want to do is I want to actually use these in pieces of information. So I know that I start out with a height of 6 feet, and what that tells me is that my position at time 0, my starting time, is 6 feet. Because it's always convenient to start at time 0. I also know another thing. I also know that I start with an initial velocity of 60 feet per second. So what that tells me is that my velocity at time 0 should be 60 feet per second. And I know the ball is getting thrown upwards, and I want to know how high it will go. This actually secretly tells me one more piece of useful information. The ball is thrown vertically upward also tells me that my acceleration function is going to be negative 32 feet per second per second. Now the reason I know this is because I know this is gravity. And I guess I would technically say that we didn't say this was on Earth, but the gravity on Earth is negative 32 feet per second per second. So these are all the things that I kind of know about my function so far. And now I want to start using indefinite integrals to make use of this information. But I also want to think about my third step in this process. My third step is to find a target. Basically, what I want to do is I want to set my goal of what I want to figure out. And since I want to figure out how high the ball is going to go, my target is probably that I want to find my position function. I want to know what this function is. And so I need to figure out a way to get there. So my plan of attack is going to be that since I want to find my function p of t, I need to figure out a way to get there. And well, what do I know? I know that if I started with my function p of t and I took the derivative, I would get velocity. And if I took the derivative of this function, I would get acceleration. And from my initial conditions, actually, I know what my acceleration is. I know my acceleration is negative 32 feet per second per second. And so what I can do is I can move back along this line of reasoning by taking integrals. By taking integrals, since it's the inverse of differentiation, I can move backward. So what this means is my velocity function is going to be the integral of my acceleration function. So it'll be the integral of negative 32 dt, which is negative 32t, and hopefully your brain is screaming, plus a constant. Well, now you can say, well, how does this function help? What's that constant? Well, let's recall another thing I remember. One of the things my function tells me is that at time 0, I'm going 60 feet per second. So this means that into this function v of t, 60 needs to equal v of 0, needs to equal negative 32 times 0 plus c. So this tells me that c is equal to 60, and I have myself a good velocity function, negative 32 t plus 60. So we're not there yet. I need to integrate this function to get my position. So recall, I just figured out my velocity function is negative 32t plus 60. And I know that position is going to be the integral of velocity. So I need to integrate this function here. So again, it's not so bad. It's a nice polynomial. So now I get negative 32 t squared over 2 from the power rule plus 60t from the power rule plus a new constant d. Shoot. Well, recall again, one of the other things I know is I know that at time 0 I need to start out at 6 feet. So this means 6 is equal to p of 0 is equal to negative 32 over 2 times 0 squared plus 60 times 0 plus d. So this tells me that d is equal to 6. So what I've got now is I've finally figured it out. I've got my position function. Negative 32 over 2 t squared plus 60t plus 6. So the last thing to figure out is how high the ball is going to go. I've got my position function. I can figure out the position at any time, but now I need to figure out, well, what time is this going to be at? So what I've done is I've graphed my function over here, and we can see my position function looks pretty nice. I start at 6 feet. I'm moving upwards, starting at 60 feet per second. The ball goes up, 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 and then it falls down. And I want to figure out here how high it goes. So graphically, I need to figure out what this height is. Now I could look at the graph and estimate it, but that's not fun. What would be more fun is to figure out what time it was happening at so that I could put time into my position function to get out that height. And the thing to think about here is, well, if I throw a ball straight up in the air, how fast is it moving when it's at its highest? So at the highest point, as it turns out, my velocity is going to equal 0. So I need to figure out when my velocity graph is equal to 0. And so what I need to do is I need to set velocity equal to 0. So I set negative 32t plus 60 equal to 0, and I solve for t. And I end up with a t value of about 1.875. I don't know why I said about. It is exactly 1.875. And then I put this into my position function. So my position at 1.875 seconds, I turn the crank and I compute this thing, and I end up with 62.25, and hopefully your brain is screaming feet. So this is how high the ball goes based on when I threw it up in the air. So that's pretty neat. One last thing before I release you to try problems on your own is the following idea. Notice that this position function is just the one we had for derivatives from before. Our force of gravity is 32. Our initial velocity was 60. And our initial height was 6. Now the reason we want to use this method though instead of just plugging numbers into a formula is because what we can do is we can actually build formulas for when we don't actually know just the initial times we start things at. We can do this for any time to figure out constants that occur at different places, not just at 0. So let's look at an example of this. Let's find the position function for a ball thrown off a 200-foot tall building if after 1 second the ball is falling at 64 feet per second. So the key thing to pick up here is the ball was thrown off, but we don't know how fast it was thrown off, and we don't have an initial velocity. What we have is we have the velocity after a second. So we do know some things. We know that the position at time 0 is going to be 200 feet up, but now we know the velocity at time 1 is 64, and we want to make sure it's a negative 64 feet per second because it's falling. But from this information, we can still reconstruct a position function. So once again, we work backwards, and we note that the velocity function is going to be the integral of our acceleration, which is negative 32 feet per second, so negative 32t plus a constant. And now using our initial condition, negative 64 needs to equal v of 1, which is equal to negative 32 times 1 plus c. So this tells me that when I solve for c, that what I'm going to get is c has to be negative 32. So overall, my velocity function is now negative 32t minus 32. I integrate this for my position function. Position is the integral of velocity, which will be the integral of negative 32t minus 32 dt. So negative 32 over 2, t squared minus 32t, and I've run out of room and I apologize, plus a constant d. And finally, using my initial condition, I get my particular solution, p of t, will be negative 32 over 2, t squared minus 32t, plus the initial 200 feet. So this one, I didn't actually know my initial velocity, but I'm still able to reconstruct and build this position function because my initial condition here tells me how to fill in my constants. As always, try the few problems, take the quiz, post a question on Blackboard, and we'll discuss this more tomorrow. Or in class whenever you read this, I guess.